the 255th National Meeting and Exposition of the American Chemical Society, coming to you from New Orleans. We are joined today by Dr. Kendamir and Dr. Dave Worley from Auburn University. They are working on a way to continuously kill bacteria on coated stainless steel. And I believe Dr. Worley, you're going to start us off.
Thank you. Yes, my name is Dave Worley. I'm a professor emeritus in the Department of Chemistry and Biochemistry at Auburn University. I've been working on antimicrobial materials for many years, since about 1980. Our emphasis has been on a class of compounds known as N-halamines, which means an organic molecule in our case, which has a nitrogen-chlorine or a nitrogen-bromine bond. The polarity of this bond is such that the chlorine or the bromine has a positive 1 oxidation state. The way these things work is when they contact a bacterial cell, the chlorine or the bromine will be transferred to the cell, and it will kill the cell by an oxidation process in the same way that your chlorination of water in a city water plant would kill organisms. Our emphasis has been to develop materials, particularly polymer type materials, that hold the chlorine for long periods of time until it's necessary for the disinfection event. These things, the chlorine is not emitted into water, for example. It is held until there's an actual contact. We have studied a variety of surfaces over the years. Our first success was on a polystyrene compound that was derivatized with one of these N-halamines, and that's being used currently in water filters to kill bacteria in rural areas where city chlorination is not possible, particularly in China, India, and Brazil. So knowing how that worked, we were able to then apply the same technology to other types of surfaces, such as textiles, gauze, things like that, and most recently to stainless steel. And we're doing this in order to perhaps develop food protection surfaces that are made of stainless steel, or medical instruments, that sort of thing. I'm going to turn this over now to Dr. Kendamir, who actually did the work in the lab.
Hi, thank you. My name is Kendamir, and I'm a postdoctoral researcher in Dr. Worley's lab. And as he mentioned that our previous knowledge on N-halamines, that using that we thought and hope to use the same knowledge and apply that onto stainless steel and tailor its antimicrobial properties. So today in the market we have stainless steel, antimicrobial stainless steel, but they mainly use a silver or copper, which are toxic to humans. And N-halamines in that case are biodegradable. In this project, our approach was first oxidize on the stainless steel surface, and then that will help us to introduce our N-halamine polymers onto the stainless steel. And here we functionalize this N-halamine polymer onto the steel with a chemical functionalization, and the bond between this antimicrobial property with the steel is covalently attached. Therefore, it's not going to be loose, and there will be stable onto the surface. Unlike silver or copper ions, they only stabilize by ionic introductions, and when they are consumed, there is no way to introduce again back. But in our case, because our compound is onto the surface, stably attached, and also the bond between the chlorine bond, which is our active compound, is stably attached onto the N-halamine compound, that we can, once the antimicrobial property of the steel is consumed, it can be regenerated easily by just applying a dilute household bleach solution, and that will regenerate the properties again, so we will have another cycle of antimicrobial steel. After studied activation of the steel, we also studied the antimicrobial properties of this newly stainless steel, and that we find compared to again other surfaces that has been in the market, that we studied the contact killing mechanism, which is when you introduce a bacteria onto the surface, counting the viable cells after a period of time, and it was only 15 minutes that enough to inactivate 6 log of bacteria, and whereas silver or copper you need 24 hours, and this was a good, very good achievement for our study. And also our system approach, the synthetic approach is one-step approach, in whereas we only introduce our enhalamine, which is antimicrobial compound, directly with a one-step. In other methods, there is a cross-linking agent requires in order to introduce antimicrobial properties, and in our way, we do not need that cross-linking extra agent. We can directly functionalize the surface with one step. So I think that's yes, that's the final. Thank you for listening.
All right, if we have any questions, we'll take them now. Go ahead and give us your name and affiliation before you ask, please. It's coming.
Hi, so it's Kath O'Driscoll from Chemistry and Industry magazine. I was interested because I've come across enhalamines before, and you mentioned this spectrum of different applications. So far, it seems that they're, I don't know, maybe niche applications. Is that because the technology is expensive? I'm just wondering, why aren't we seeing more of these products on the marketplace already?
Yes, the only thing that's on the marketplace is the polystyrene beads that we developed that are being used for water disinfection in China and India and so forth. It's just extremely difficult to find somebody that'll take a university project and run with it. It's what I've found. As a matter of fact, in my day, I visited hundreds of, many Dow, all the big companies. Very difficult to deal with these people when it comes to trying to get some research commercialized. You need to go with a small startup company, and that's what we did to get the first thing. But like the stainless steel, we've just now come out with this, so hopefully we'll get lucky and somebody will contact us and want to run with the ball.
Could you say something about the effects on, I guess, antimicrobial resistance? You would think that with this being such a big issue, that products like these...
I know for a fact that there is one compound that has been used in the medical industry, and that they studied that it's another type of enhalamine compound, and they studied their resistance, and that they find that is actually not resistant to bacteria. So that would, in our cases, that would not be a problem.
Yeah, so that's why I'm thinking this should be a big driver for people to actually develop some of these products.
Yeah, the main killing agent is the chlorine. I mean, an enhalamine is just a way of stabilizing chlorine for a long term so that it's not lost through evaporation or through washing processes.
But how does the cost compare with, say, the products like, say, silver incorporated or you know?
Well, we're finding, as she said, 15-minute contact time to get a 6-log reduction of Staph aureus or Escherichia coli, whereas silver, from what we've seen in the laboratory testing some commercial silver, actually it wasn't a steel, it was a gauze product, but it was taking 24 hours to do similar disinfection. So we think this is a big advance in the field.
What did you need to do? I think you mentioned some pre-treatment of the steel that you need to do in order to attach the inhaler?
Okay, that's a good question. That's the biggest disadvantage you pinpointed here. You have to treat the surface first with something to put oxygen atoms, well actually either with a negative charge or an OH type functionality on the surface, then we react with that directly with our copolymers. So if you want to put O- on the surface, or OH, the way that's been commonly done by people working with stainless steel is to use something called a piranha solution, which is a mixture of hydrogen peroxide and sulfuric acid, which is not good. We're looking for alternative routes to do this, oxygen plasma, something like that. Nobody's going to treat a food preparation surface with sulfuric acid and hydrogen peroxide. We realize that, so we're looking for some way to create these oxygen atoms or negative ions or OHs alternatively that could be done, say, in the steel processing before the actual countertop is produced.
Do you have any thoughts on how that might be achieved? I know that the release mentioned something about ruggedizing the surface of the stainless steel as well, which I guess would improve the attachment. How much have you been able to attach so far?
The attachment is not the problem, but if you look at all kinds of reports on stainless steel functionalized surfaces, that everybody needs to, it's very difficult to functionalize inorganic substrate and with organic chemicals, so you had to have a type of treatment before because of the creating the, OH groups on the surface, and there's different methods that has been studied, and we think plasma treatment could be a good way, to start to study. And but there is no other research that you will find that they didn't do this because you have to do it basically.
We found that it takes 1 times 10 to the 17 chlorine atoms per square centimeter of surface to get the type of kills we see. Prior work has not been able to achieve that.
Thank you.
Ben Felser from Chemistry World magazine. What do we know about the physical properties of your functionalized surface? Do we think it is hardy enough and tough enough to be used in industrial food preparation?
Well, we found that the only testing we've done along those lines would be exposing it to water, flowing water, that sort of thing. We found that we could wash the surface 5 times, and even though you lose some chlorine, you can then rechlorinate the surface by exposing it again to dilute household bleach. So the actual polymer itself is not coming off the surface. So it would be an easy process to periodically treat the surface with dilute bleach. We're only using like 10% of a bleach solution. You don't smell the chlorine even at that level. It's a low concentration, so it would be fairly non-corrosive.
And what is the trigger mechanism that causes the bacteria to release the chlorine and then kill them off? Would you also see the same thing if you put a piece of steak on this surface? Would that also trigger the release of chlorine?
Good understand.
What is the trigger? So I think the mechanism, so this is not, we are a chemist, and that is more microbiology type of study, but so far we know that the mechanism is once the bacteria came in contact, this is oxidized, the chlorine is positive, and so that positive chlorine is basically reacts with the bacteria and damages the bacteria cell. So that's the mechanism that we know.
Yeah, you have to bump into the surface, the bacterium itself, and when it does, the chlorine that's bonded to nitrogen is simply transferred to a receptor site on the bacteria, probably another nitrogen or a sulfur, and then it oxidizes it and that kills the cell.
Right, so there isn't a particular chemical process that causes release from the polymer. It's merely the fact that the stabilized and is there available to react.
It will only release when there is, like come in contact with the bacteria. So that's when the release happens. Yeah.
Excellent. Thank you.
Bill Westlick, American Chemical Society. As I understand it, if I understand it correctly, the polymer is actually chemically bonded to the stainless surface.
Correct.
Okay. Essentially, the question here is would you have any particular reason to worry about the abrasion resistance of the surface? Because obviously, stainless surfaces or any food handling surfaces need to be cleaned once in a while.
We don't think
you just
routine.
wash it off, and you never really have to resort to anything like scrubbing or anything of the sort. Because I don't imagine that would do much for the coating of the surface.
I think the only thing that would cause the coating to come off the surface would be some mechanical effect or some solvent, for example, that dissolves the polymer coating. But water is not going to do it, that we know.
But you feel that just washing it with water under just standard food handling circumstances is an adequate way of doing it, because it seems like the answer for a lot of things. Of course, you don't go and start cutting up meat on a surface like this, because that will score the surface.
Yeah, if I was in a food processing plant or something, I'd wash off the steel with water, and then I would secondly subject it to a dilute solution of bleach and recharge the surface again at the end of the day, say, then the next or the first of the day, and then it should last. Well, it's going to last a lot longer than a day. Now, there are other things besides bacteria that can kill with chlorine, such as organic matter, blood, things like that. So that can take the chlorine, but it's not going to affect the polymer itself on the surface. You'd have to rechlorinate after if you had a lot of exposure to organic materials like that.
Thank you very much.
Okay, if we don't have any more questions, I'd like to thank everyone for coming. Let you know that the archived version of this session will be posted shortly at bit.ly/ACSLive_NOLA. And our next press conference is at 1 p.m. We would love it if you join us to hear about making fragrances last longer. And thank you very much.